And now moving on to number 4, we are actually going to now do our first proof that involves perpendicular lines. Okay, and we're going to have to recall some of the theorems that we've covered in the past that deal with the definition of perpendicular lines. So the first thing I want you to do is correct your sheet, because you'll notice that there are some misprints. There are some funny symbols. A lot of symbols were a little rectangle with a question mark in them like that. Those are supposed to be the symbol for perpendicular. Okay, so wherever you see that funny symbol, which is here and here, as well as in statements 1, statement 3, and in the reason for statement 2, just overwrite that funny symbol with a perpendicular sign so we don't get confused in terms of what that symbol means. Okay, so now let's start with the proof. Let's take a look at the givens and let's look at the diagram. So we are given that AB, line segment AB is perpendicular to line segment AC. Okay, so AB and AC are perpendicular. We often, AB and AC are perpendicular, so we've got AB and AC are perpendicular. Sometimes we're going to make ourselves a little right angle sign because that's going to help us remember that those two lines are perpendicular. Also, line segment AC and CD are perpendicular. So AC and CD. So over this number 2, I'm going to put a little symbol there to remind myself that those two lines are perpendicular. And at the end of this all, we're going to be able to prove that AB, this horizontal line segment, and CD, this horizontal line segment, are parallel. Okay, so that's pretty amazing that we can prove that they're parallel just because we have two line segments, each perpendicular to the same line. Let's go ahead and let's start. So we've got AB is perpendicular to AC. That was one of the givens. And then we're not given the second statement, but we're given that the reason for the second statement is that being perpendicular implies right angle. Well, I would say it a little bit better. I would say this is the definition of perpendicular lines. Okay, you may remember we covered the definition of perpendicular lines, that two lines are perpendicular if they meet in right angles, if they intersect in right angles. So if AB and AC meet, are perpendicular, they meet in right angles, and we probably need to specify one of the angles formed by their intersection as a right angle. Well, we're being helped along here by the fact that the only angle in this intersection that's labeled is angle 1. So probably the person who came up with this proof wants us to use angle 1 as the right angle. So I'm going to say that angle 1 is a right angle, because that follows from the definition of perpendicular lines. And now let's go up to here. AC is perpendicular to CD. AC is perpendicular to CD. Well, why is that? I hope you remember that was a given. Okay, it's given up here. So we can easily just write in given for that. And angle 2 is a right angle. Well, we already know that's because of the definition of perpendicular lines. So if you take a look at AC being perpendicular to CD, you'll see that the only labeled angle from that intersection is angle 2. So we know obviously angle 1 and angle 2 are the important angles here. So now we have the next statement saying the measure of angle 1 equals 90 degrees. And also, for the same reason, the measure of angle 2 equals 90 degrees. Now you have to remember that we've already said that each of these is a right angle. So how do we get from it being a right angle to an equality that says it is equal to 90 degrees? That is the definition of a right angle. Okay, we said at one point, a few days back, that we define a right angle by being an angle whose measure is 90 degrees. So in this case, we've said they're right angles. We can make the statement they're both equal to 90 degrees. The next statement and reason we're given, we don't have to fill in anything here, but we still should understand what's going on. The addition postulate of equality is being used to come up with this statement, that the measure of angle 1 plus the measure of angle 2, and there's a little measure missing in there, equals 90 degrees plus 90 degrees. So how does the addition postulate of equality give us that? I'll give you a second to take a look at this. Well, I'm hoping you remember that one of the shortcuts we said we would permit is we could add together the left side of equations and the right side of equations. So if we add the left side of these two equations together, we get measure of angle 1 plus the measure of angle 2. And if we add the right side of these equations together, we get 90 plus 90. Now, we could have just put 180 here, but in this particular proof, they want to actually use addition as a separate step. So if we use addition as a separate step, all we're saying when we do that is we're just adding up the 90 and the 90 to 180. Okay, it's just using addition. It's not the addition property of equality. Sometimes I don't think a step like this is really needed, but different people do proofs in different ways, and you have to be flexible. You have to kind of be able to figure out what it is that they wanted to say here. And since they did not add the 90 to the 90 in this statement, it's obvious that they want to add it in another statement. So that's just using addition. Okay, and we're only doing it, we're just using addition as a, not as a property, but as a as an operation. Okay, so this is addition as an operation, not as a property. Okay, now remarkably, we're getting near the end of the proof. This again, that 180 degrees implies supplementary angles is the definition of supplementary angles. So I would give you in a quiz or a test that this is the definition of supplementary angles. And what do you think we're going to be saying here? Well, if the measure of angle 1 plus the measure of angle 2 is 180, then that means that angle 1 and angle 2 are supplementary angles. So we can say that angle 1 and angle 2 are supplementary. So let's take a look in the diagram. What that means is that these two angles are supplementary. Well, what kind of angles are these two angles? That's right, they're same side interior angles. So now we're saying that same side interior angles are supplementary. And remember the two lines, we could extend this line out. It makes it a little bit easier to see that we actually have two lines here cut by a transversal. Okay, I hope that makes it a little bit easier to see. There should be just a little bit over here. That now we're talking about same side interior angles being supplementary, and we know from the converse, okay, the converse of the same side interior angles postulate, that if two same side interior angles are supplementary, then the lines are parallel. So again, if two lines are cut by a transversal so that a pair of same side interior angles are supplementary, then the lines are parallel. That's the full statement of the converse of the same side interior angle postulate. So we can then conclude, since they're supplementary, that angle A is parallel, rather AB, line AB, is parallel to line CD, or that line segment AB is parallel to line segment CD. This is an important proof. It tells you that two lines, which are each perpendicular to a third line, must be parallel to each other. So if you did not get this proof the first time around, or if there's some things about it that are unclear, I suggest you watch this video again so that you are sure you understand every step and that you understand what was given and what the conclusions are.